Hello everyone and welcome to today's session. My name is Mark Westerway. I am a driving simulator engineer at ViGrade and I will be your host for today. I'm joined by Martino Minen, who is our sound expert here, and later he will be talking in detail all things sound and simulation. And after this, he will be available to answer any questions that you may have during the presentation. Before we get started, I should mention that this webinar will be recorded and the video will be made available on our webpage soon. So you can check that out post-presentation. And also, please make sure you are currently set to mute to avoid any interruptions. As you can see, we have a lot of things to talk about today, but to summarize the agenda, we will be talking about the entire process of going from sound reality to sound simulation, and how we at ViGrade are providing a complete solution to this problem. After the presentation, we'll have a Q&A session. Please use the chat function to send your questions directly to the WebEx chairman host, who will collect all of the questions and we will answer them at the end. So what actually is the problem we are trying to solve? Well, car manufacturers are constantly facing new challenges. Nowadays, when people buy a car, they expect all aspects of the driving experience to be pleasant and safe. We as humans have been hardwired to use all of our senses to perceive our surroundings. And this holds true even when driving, whether it be conscious or subconscious. The driver and passengers are using sound as an indicator of what is happening around them. Since sound is so influential in the driving experience, engineers and designers need to be able to accurately replicate real acoustic conditions. And we at ViGrade are meeting this requirement by providing a complete solution that can reproduce all the sound information you would expect to experience in reality. So when it comes to designing the perfect sound, there are a few key ingredients that need to be taken care of. First, acoustic sources must be accurately identified and recorded. This serves as the foundation for everything that follows. Then, the acoustic interior environment must be simulated properly, and the sounds must be synchronized with other simulated cues, such as the visual and the motion. And this can only be achieved by using a real-time acoustic model. Finally, some amount of tunability must be possible, so you can fine-tune the sound sources based on the driver's feedback. And these key ingredients allow engineers and designers to experience the sound of a vehicle without even having to build a prototype, thus, of course, saving time and reducing costs. And it's not even just engineers and designers who can benefit from this solution, but also drivers, manufacturers, and suppliers. So here's a short list of why we believe our solution is a good solution. First of all, our sound solution can be used in all ViGrade driving simulators, all the way from the smallest simulator being the desktop to the biggest being the DIM. The sound experience in the simulator matches that of reality, which improves the simulated driving experience and immersion, and additionally allows for the testing of acoustic perception, as well as evaluation of the impact of acoustic sound design on the vehicle occupants. Furthermore, it's possible to complement the sound experience by adding VI shakers to cover the full frequency spectrum. And in summary, the ViGrade's Automotive Sound Experience helps customers bridge the gap between testing and simulation. So now I'll hand over to Martino, who will talk in more detail about exactly how we're doing all of this.
Hello everybody, welcome to the webinar. My name is Martino Minen, I'm a sound engineer for ViGrade. And let's start directly with the first slide. This slide here explains how the frequency spectrum coverage is provided by the various subsystems in the ViGrade simulator. On the low end, we have the active seat and the dynamic platform, flagship of the VI technology. And moving up the ladder, we have the shaker system, which is responsible for covering the transition between low frequency and high frequency. And the right end of the spectrum is covered by acoustics, which is provided by SimSound, which is a HBK software, our sister company, HBK. So here's a quick overview on the workflow. Essentially, as in many scenarios, we start from a data acquisition. So we pretty much record and data gather, and then we process, and ultimately we make a model, and then we play it back during the simulation instance. As Mark mentioned, our technology is applicable to every kind of simulator we provide throughout the product line. So starting from the desktop, moving up to the compact, the static, and finally the DIM. It might come in different shapes, but the source is always the same, and it's a very flexible system. It provides high quality sound rendering throughout the whole chain, which also makes it an advantage basically. So let's start from the first step, which is recording. And we use binaural recording for various reasons. The first one is using binaural, you have sound directivity embedded in your data. So that very much respects the sound environment the driver has to be put in, and the driving position. So again, the simulator is really oriented to reproduce reality, so exactly what the driving experience is like. And using this type of technique allow us to be very maintain high fidelity at the end. So the driving position is very important, and also the interior absorption is important. You can either use the torso head or the binaural microphones directly on the driver's ears. External contributions also are quite important. We at VI Grade think that tires are also very important, especially for high performance drivers. We also provide external contributions, external sources using external microphones such as wheel and exhaust explosions. I will get maybe in a little bit more detail later on this. So this is basically a quick overview on the technology we use, on the gear we have. Aside the acoustic data, we also record the telemetry of the car. This is very important because the correlation between acoustics and telemetry allow us to make the model. So we use a bunch of different sensors for RPM, optical sensors, very quick, very reliable. For the engine phase, we use an electromagnetic clamp. And for electric vehicle mainly, we use a triaxial accelerometer directly on the gearbox. The sampling rate is very high, so it's 65,000 hertz, and everything is recording in the same data quire. If you can see on the right-hand side of the slide, the Line XI, which is pretty much a big hard drive, portable hard drive, very rugged, records everything into one data file. The reason why we do that is because, again, acoustics require a lot of a very high sample frequency, much higher than a lot of other different type of data. And we record everything in analog to avoid digital lag or digital frequency mismatch or sampling mismatch. Of course, campus telemetry is recorded, and everything is stored in the same data file. So to create a sound model of the car, we first have to identify the various components of the sound that a car produces. So the first one, obviously, is the engine. So engine sound is parameterized with RPM. So we use RPM to parameterize engine sound, and then later on extract harmonics. That is one part of the sound. The other part is the engine masking noise. So everything that is non-harmonic will also be included in the model, and we call it engine masking noise. And also, in this case, the parameter is RPM. The vehicle masking noise is road and wind, and the parameter is vehicle speed. So there's a lot of the sound in the car is due to the vehicle, to the excitation of the chassis, and the wind blowing over the windscreen. So we absolutely need to include that in the model, and we do that throughout vehicle masking. External, as mentioned before, we have a bunch of different external contribution. Tire squeal and brake squeal, which are parameterized by lateral tire slip and longitudinal tire slip. Then exhaust explosions, which can be triggered by downshift or different type of engine logics that can be incorporated into the simulation. Remaining on the recording topic, we have to make the car sound. So we have a list of maneuvers that help us gather the data that we need, and most of them are just measured on a straight. For engine harmonics, we do a couple of different run-ups at different throttle positions to characterize in detail the various the change in harmonics of the car according to different loads on the engine. And in this case, we use the throttle position because it's driver input and it's easy to apply to the test and can be repeatable. The engine masking noise, it comes from neutral run-ups. This because we record a marching car. Most of the time we record a marching car. So to avoid the vehicle masking, we record a neutral run-up, and we use the non-harmonic part of that test as engine masking noise, total engine masking noise. Vehicle, a straight constant speed measurements or neutral cost downs. These are two different ways that can provide the same result at the end. So the vehicle masking can be recorded at different speeds, or using a neutral coast down, basically letting the car slide down to pretty much a standing still position, and then a process over this this data has to be done to gather segments of sounds that correspond to different speeds, and that will ultimately serve as vehicle masking noise. For the external contributions, the tests that we usually do are essentially a fixed steering angle, incremental speed to make the tire squeal, or fixed speed and incremental steering angle. And exhaust neutral run-ups usually rev up the car and make the exhaust explosions. Okay, let's dive into the processing. So first of all, the first thing that we absolutely need to do is decompose the harmonics from our data. So how the system works is essentially we have a very straight direct correlation between the harmonic variation and the RPM curve, and we pretty much set up the program to follow the RPM curve and set up the filter, so it's a dynamic filter to extract, to cut out the harmonics from our recordings. This is absolutely very important, and you ultimately end up with having a data file that stores your harmonics at different loads in different gears. This is a very important step here. This is also will help us having the masking noise later on. This is the decomposition player. So after we have extracted the harmonics, we can pretty much check and listen to what was the original sound that we recorded, the engine sound and the masking sound. So essentially, when we remove the harmonics, what is left in our data is the masking, and we can use that masking for our purposes. I think we can listen here. just listened to was a example of decomposition from a 100% run up, so full throttle. And the first sound that we listened to was the original recording, so everything all together, exactly how we recorded it. The second one was just engine harmonics, and the third one was what was left, so the engine masking. You can clearly see that the engine masking has been removed of a lot of content, and that content is basically our harmonics, which was the second sample. So let's talk about engine masking noise. We use another software from the HBK software bundle to extrapolate the masking noise. So as mentioned before, from a neutral run-up, we extrapolate the harmonics, and what is left is the masking. And we pretty much split up this masking sample into various sound segments, which are then assigned with a different RPM value. And this will be arranged into an array of samples, and according to the RPM value during the simulation, the matching sound will be played, and this creates a nice progression and an interactive feeling to it. Let's move on with the vehicle masking noise, which pretty much follows the same principle as the engine masking noise from our. This is an example of a neutral rundown. So we have a very long sample. Sometimes it can be up to a minute long, depending on how fast we were going. And we use pretty much the same program to split up and get these sound segments at different at different speeds values. Maybe I can add that the vehicle masking noise is essentially wind and road together, and we do neutral run-ups, so we have the lowest engine contribution in our data. So external, we're still in the processing step. How we process external, we use BKconnect, which is probably the biggest HBK software. It's very powerful. It allows a lot of it allows the user to do a lot of analysis, a lot of processing, and it's very much. It has a nice layout, easy workflow, so it works very well. How do we process tires? We have as mentioned, a microphone directly on the tire, an external microphone, and we pretty much do a frequency response function between the external microphone and the internal microphone for both channel, and we use that as a filter on the external microphone, and then use that processed file into the model to have that sound contribution from that particular wheel on that particular road doing that type of conditions. So the reason why we do that is because most of the time when the tires are squealing inside the car, you don't really know where which tire is squealing, and obviously it's hard to make just one tire squeal. So when the car starts sliding, all the tires, so pretty much all the tires start squealing. So it creates a very confused sound directivity issue inside the car. We wanted to make a step forward and identify which tire was squealing, and since we are very, very close, we're very keen to reproduce reality, we wanted to record that very tire and put that into the model. So the result is basically wave files. Again, this is an example of tire squealing that has been processed for the left channel. Maybe a note on this, with very, very noisy cars, it's very hard to isolate the tire squeal from the engine noise. So it's a type of process that works many times, but you need to have a very good squeal to make it work. Otherwise, very noisy cars you will always have engine contribution in your external recording. So it's going to be hard to isolate the tire squeal, and but this is an example of how it could be done. think we can listen to this. So this example basically shows how a tire squeal would be heard from inside the car if you can possibly shut down every other sound source in the car. Imagine a silent car just squealing on one wheel, and you are at the driving position. This would be the sound that you would hear from that tire. So I think we can move on to the assembly finally. So once we have our bricks to build the model, then we can assemble each and every part into a one sound model. And we use a program called VSound to do so. We're still talking about HBK technology. And as you can see here, you can very easily understand that we have a tree diagram that contains our engine contribution, our masking contribution, and other type of stuff like custom triggers and so on. The calibration. So we stepped into the replay part of our workflow. The calibration is also a very important topic into the sound simulation. So basically, a calibration is a compensation of the system to have the most linear frequency response in the sound environment that we put that in. So the way we do this is we calibrate the microphones first, and the microphones that we use for the calibration are very similar to the microphones that we use to record the actual car. So first of all, we calibrate the microphone if it's needed, and we have a microphone calibrator to do that. And then we move on to the speaker system calibration, which is essentially our sound system inside the simulator. And it's an automatic process. So SimSound, it's capable to auto-calibrate the system. What it does is basically outputs a pink noise, which is a noise with the same amplitude at all the frequencies, according to some loudness curves. And the microphone picks up the pink noise from each and every speaker. Of course, we do it one speaker at a time. So it will record the output from the speaker, and will automatically calculate a Q curve to have the most linear response possible. So if there are any absorptions or any amplification at different frequencies, the program will try to compensate that for it. Can you guys hear me? I think I was muted for a moment. So as we're saying, the Q curves, the program will try to compensate for any attenuation or amplification due to the sound environment. And of course, you can store the calibration curves. You can apply them to the same cockpit basically, but the system can store multiple EQ curves. So pretty much, if you want to change the system, or you make some, or you actually build a different markup, you can have a very easy interchangeable system due to the storage capability of the software. So I think we can move on from calibration to simulation, and here's where the party starts. Basically, when we have our model, we are exported to the SimSound database, and SimSound is very simple but very effective application. It basically replays our model, and it will power up the model using the data stream that we provide from our solver PC. So basically, what it does is shows you the real-time monitoring, so the RPM value, the speed value, the throttle position, what gear you in, and the custom trigger activation, which is our external sounds, our essentially added sounds that we talked about before. It's very simple but effective, and also allows level monitoring, so you know at what level your model is being pretty much exits the software. And of course, it allows you to change model from the database. So you can easily, quickly choose between models doing your work on a simulator. Still talking about simulation, here's TotalMix. TotalMix is basically our digital mixer, and it's one step closer to the sound system after SimSound. So basically, SimSound outputs the signal into TotalMix. TotalMix is essentially the controller of the interface that we use. We use RME interfaces, which are ASIO compatible. So they provide the digital audio buses for SimSound to output sound. And again, here you'll see in the picture a bunch of different faders. They pretty much do the same thing, but it might look a little bit complicated at first, but it's very simple to use, very easy to understand, and it allows you a huge number of different activities you can do on it. You can handle the intercom, you can group different signals, you can use smart buttons, so you can quickly access or change levels and all this type of stuff. And it's basically our last our last platform before going back to the analog world. So TotalMix, it's a very powerful tool. It's absolutely necessary for the system, and it works flawlessly. Again, when we exit the sound interface and we go to the system, of course, we provide, especially in higher levels of the product line. So basically, starting from the compact, a surround sound system. Surround sound systems can come in various different shapes. Probably the most known is the 5.1 system. Here we have a very simple picture that exemplifies that. And the SimSound, so the audio rendering, the audio engine is capable of rendering our binaural recordings into a surround format, which is absolutely crucial, important, and not trivial at all to do. So pretty much BNK has a lot of know-how on how to render sound, and they develop their own algorithms to render and code binaural recordings into surround sound. So basically, the program knows if you set up correctly and set up the audio system in the program knows how much of the signal has to be sent to each and every speaker. So this is very important. And again, having a calibrated system, it allows you to have a very good result at the end. So very immersive and very precise, I would say. And again, here we have a comparison of the output from the model and the original recordings that are essentially triggered by the same telemetry data. So the telemetry, the sounds that you hear, I think in the first sample are the original car. From that test, we recorded, I recorded the telemetry, so the vehicle speed, RPM, and so on. And then I sent the same telemetry to the model once I have assembled it, and I recorded the output and put the two together like this, so you have a quick comparison between the two. I think we can listen to this. The first, well, I'll let you guess what was the original car and the model. But since you can't reply, I'll just tell you. So the first one was the model. The second one was the real car. As you heard, they were very similar. So we have a very compliant. Um, in the original car, you will always have some type of real scenario, real life scenario type of sounds, like the little bumps and little scratchy sound inside the car due to I don't know, maybe the seat moving, stuff like that. This was a very fast and noisy car with a beautiful sound, I would say. But the program is capable to capture the I would say 90% of it. Remember, it's still a synthesis, still a simulation, but the result, it's very outstanding as far as um, close to reality type of result. So it's very compliant. Uh, it's very efficient, as I said. You guys let me know in the comment later on what you thought about it. Again, this is still part of the comparison, and we have a simple spectrum analysis of the two. These are the same two, the two very samples that we heard before. So we have the original left and right and the model left and right. You can clearly see that the harmonic content is pretty much the same. Um, in the original recording, we might have a little bit more of road contribution, because the road we recorded this test on was slightly rougher than the road that we used for vehicle masking. But as you can clearly see, the harmonic content follows essentially the same path, and also the amplitude is very similar. This again proves that the system works, and we're very happy about it. The slide, it's a quick overview on the shaker system, as just to mention it. Basically, the VI shaker system, it's sort of we wanted to again cover up the transition from low frequency dynamic and acoustics. So the shaker system actually provides that. Shakers are essentially inertial shakers, so it's a silent subwoofer, so if you want to call it. It's basically a transducer which has a little piston inside, and this piston moves up and down according to the frequency that you send it to. And the amazing thing is we developed the system, and we're very happy about it, because it is strictly it directly depends from the VI carrier time model. We pretty much synthesize the signal in real time, and it's highly influenced. It's basically created by the model. So depending on which type you have, you will have a reflected output from the shaker system. It's very fast. It's very, I would say, it's very reliable as far as we could see. And of course, it's matching the audio output. So, for example, curves, you would have the sound contribution of the curves and the high frequency mechanical contribution from the shakers going over that curve. Again, the amazing thing is you don't need to record absolutely anything to have this in your simulator. You just need to implement the shaker system, and then you can start using it from your car real-time model. So I think we can conclude here. There's a bunch of papers that our customers provided to us, and yeah, basically, again, proves and shows that the system is very capable, and customers are very happy about it. This is an example of Volvo, which basically says that the cars that have been developed with the simulator are the best Volvo cars ever. And I personally agree. They are very good cars, and definitely a huge step for Volvo. So again, here's a bunch of conclusions on what we just said. reproducing the vehicle sound information, simulating the acoustic environment and in a real-time scenario. And this ultimately helps bridging the gap between testing and simulation, sometimes even more than some people might think. But sound is really, really important. If there's something wrong with the sound, you hear it straight away. If it's good, it will enhance your simulation up to 1,000,000, and it's a very important cue to have. Also for high performance driving, since the wheels again are very important for the driver to know where they are. And yes, so this ultimately concludes our presentation. If you're interested, please check out the link below or let me know in the comments. I will be happy to answer any question.